Hey everyone, welcome back to Miss E's Math, where we break down college-level calculus into simple visual steps. Today we're exploring Maclaurin Polynomials, a special case of the Taylor series. And then we're looking at how you can use the Taylor theorem to estimate the accuracy of a polynomial approximation. By the end of this video, you'll be able to write a Maclaurin polynomial and use Taylor's theorem to bound the error of your approximation. But first, we need to define the Maclaurin polynomial. Maclaurin polynomial is a special type of Taylor polynomial centered at 0. Here's the general form of the nth degree Maclaurin polynomial for a function f of x. Please notice this is very similar, but instead of having x minus c raised to the n power, we have just x to the n because c is 0. So it's almost the exact same thing as our Taylor polynomial, except now c is equal to 0. So a Maclaurin polynomial is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x to the second plus f triple prime of 0 over 3 factorial times x to the cube plus all the way to f of n derivative of 0 over nth factorial times x to the nth degree. For this example, we're going to find the Maclaurin polynomial p of 4 for the function f of x equals to the natural log of x plus 1. Step 1 is to find the first 4 derivatives of f of x, which is the natural log of x plus 1. Our first derivative is equal to 1 over x plus 1. Our second derivative would be equal to negative 1 over x plus 1 quantity squared. Our third derivative is equal to 2 over x plus 1 quantity cubed. And then finding our fourth derivative, the last one we need for the Maclaurin polynomial, we get that our fourth derivative is equal to negative 6 over x plus 1 to the fourth degree. Now that we found our derivatives, we're going to evaluate each of these derivatives at our center. And since it's a Maclaurin polynomial, our center is 0. So f of 0 will result in an answer of 0. Our f prime of 0 will give us an answer of 1. F double prime of 0 is equivalent to negative 1. Our third derivative evaluated at 0 will give us 2. And our fourth derivative evaluated at 0 is equal to negative 6. Then putting that into our Maclaurin polynomial form, we get our p of 4 of x is equal to 0 plus 1 times x minus 1 over 2 factorial times x squared plus 2 over 3 factorial times x cubed plus negative 6 over 4 factorial x to the fourth. Now let's simplify this down so we end up with our Maclaurin polynomial p4 is equal to x minus x squared over 2. And then let's see what 2 over 3 factorial simplifies down to. If I distribute out the 3 factorial, that's 3 times 2 times 1. The 2's cancel out and leaves us just a denominator of 3. So we can write that as x cubed over 3. And then I can do the same thing with negative 6 over 4 factorial. Since 2 times 3 is equal to 6, I can cancel out the 2 and the 3 in the denominator of 6. That leaves us with negative 4. So the last term is negative x to the fourth over 4. And that is your first Maclaurin polynomial. Maclaurin polynomials are super useful when your function is easily differentiable at 0 and you're approximating near 0. Now let's use the fourth Maclaurin polynomial to approximate the value of the natural log of 1.1. Since the natural log of 1.1 is equal to the natural log of 0.1 plus 1, I'm going to use the Maclaurin polynomial we found in the last example to approximate this. So I'm going to do the Maclaurin polynomial of 0.01, which is 0.01 minus 0.01 squared over 2 plus 0.01 cubed over 3 minus 0.01 to the fourth over 4. Now I'm just going to punch that into my calculator, and I end up with 0.095308333. And that is our first approximation with Taylor polynomials. Your turn. Pause the video and try working on example number 5. Example 5. Use the third Maclaurin polynomial for y equals sine of x to approximate sine of 0.1. Okay, so I need to find the first three derivatives of sine of x. So derivative of sine of x is cosine of x. The derivative of cosine of x is a negative sine of x. And the derivative of negative sine of x is negative cosine of x. And since I'm evaluating this as the Maclaurin polynomial, I need to evaluate each of those functions at the center of 0. So f of 0 will give us 0. Cosine of 0 degrees is equal to 1. Negative sine of 0 degrees is equal to 0. And negative cosine of 0 degrees is negative 1. So using our Maclaurin polynomial formula, I have p of 3 of x is equal to 0 plus 1 times x plus 0 over 2 factorial times x squared plus negative 1 over 3 factorial times x cubed. Simplifying that down, I have P3 is equal to x minus x cubed over 3 factorial, and 3 factorial is 6. Now I'm going to evaluate this when x is equal to 0.1, and that'll give us 0.1 minus 0.1 cubed over 6. Again, I'm going to punch this into my calculator, and that gives us approximately 0.09983333. A calculator tells us that the sine of 0.1 is approximately 0.0998334. So our approximation is very close, but how can we guarantee how accurate it is? That's where Taylor's theorem comes in. It tells us the error between the actual function and our polynomial. Taylor's theorem states if f is differentiable through the order n plus 1 on the interval I containing c, where c is the center, then for each x in the interval I, there exists some z between x and c such that, so z is between our x and our center. Now, it might be written as e is between x and c, or e is between c and x, depending if x is less than your center or greater than your center. Then you could conclude the following thing. So r of n of x, our remainder, is going to be equal to the absolute value of f to the n plus 1 derivative of z divided by n plus 1 factorial times x minus c, or x minus a, or your center, to the n plus 1 degree. So notice this is the first unused term in our Taylor polynomial, evaluated at z, where z is some number in between x in our center. So example 6, we're going to determine the accuracy of the approximation we found in our last example. So remember, it was very close to the actual, but we need to figure out how good is this approximation. So recall that we went to the third derivative, so we found p of 3, so we need to find r of 3, which means we need one more derivative. So since the third derivative is negative cosine of x, the derivative of negative cosine of x is sine of x. Our error is going to be equal to the absolute value of f to the 4th degree, because if I take 3 plus 1, that gives us 4, evaluated at z, times by 3 plus 1 factorial x to the 3 plus 1 degree. So this is, you would probably actually write this as f to the fourth derivative of f evaluated as z divided by 4 factorial times x to the 4, because since we did the Maclaurin series, our center is at 0. Now, since this is our error, we want to find our 4th derivative evaluated at z, and we want z to be the maximum value that derivative could evaluate as on that interval of z, on that interval where z could be. Now remember, z is going to be between our center and our x. In this case, our center is 0 and our x is 0.1, so z has to be some number between 0 and 0.1. So if z is exactly 0.1, that would be our maximum for that sine function, because remember, from 0 to 1, our sine function is increasing. Since the maximum value of sine of z between 0 and 0.1 is sine of 0.1, we could say whatever that value is, we don't know what that value, but that value of sine of 0.1 needs to be less than 0.1. So that makes logical sense that we could conclude that the sine of 0.01 would be less than 0.1. And so I'm going to change my error up here from a equal to a inequality. And replacing our fourth derivative of z with 0.1, I could get that my error is equal to the absolute value, is less than or equal to the absolute value of 0.1 over 4 factorial times my x is 0.1 to the 4th degree. Okay, and then I just evaluate this right-hand side of this inequality using my calculator. 0.1 times 0.1 to the 4th gives us 0.00001 over 4 factorial, which is 24. If I divide that, I get 0.0000042. That is very, very small error, less than half of a millionth, which would be very good in approximations. So to evaluate tan theorems, the big takeaway is that this 4th degree or this nth degree of z is our maximum value on the interval that z is located on. This is powerful stuff. With just a few derivatives, we can approximate complex functions to high accuracy. And Taylor's theorem gives us a mathematical way to say how good our approximation is. This technique is used in physics, engineering, and even computer graphics, wherever you need a fast estimate of a nonlinear function. To recap, the Maclaurin polynomial is a special type of Taylor polynomial centered at 0. We use Taylor theorem to estimate the error, and we saw that the approximation was incredibly accurate. Thank you for watching this video. If this video helped, give it a like and subscribe to stay updated with all things related to calculus. And let me know in the comments, what calculus topic would you like to see next?